Next function that we're going to discuss are going to be quadratic functions. So quadratic functions in general, as you remember, are defined as a x to the second plus bx plus c. And we put this condition that a is never 0. Otherwise, you get a linear function. You know, we're not interested in linear function. We're interested in having a quadratic function. Well, as you remember, if a is positive, if the leading coefficient then you have your graph opens up. But if the leading coefficient is negative, your graph opens down. In either case, the domain of the function is from negative infinity to positive infinity. And as you can see, the function is continuous everywhere on its domain. Negative infinity to positive infinity, or R. In general, we can generalize the idea to any polynomial function. A polynomial function is defined as p of x equals to a sub n x to power n plus. So the way that you read this, a sub n, this is just a number, numerical value. Your x is raised to nth power plus. The next term, a sub n minus 1 times x to power n minus 1. Another number. We read this as a sub n minus 1, which is just another number, times x to power n minus 1. You continue this process. You add as many middle terms as you want. A sub 2, x to power 2. A sub 2 is another number. Then a sub 1, x to the first power, plus a sub 0. A sub 1 and a sub 0. Any polynomial function is continuous on its domain. Some examples of polynomial functions are as follows. F of x is equal to x squared plus 2x plus 1. We remember this function as a quadratic function. G of x is equal to 2x to the third plus 3. H of x can be written as 5x to the seventh plus 2x plus 1. I of x can be written as x to the power 100 plus 5x to the 11th plus 3x plus 9. So these are examples of polynomial functions. If you use Desmos or any graphing website, you can see the continuity of these functions. There are no gaps in the graph of these functions.